All right. This is Introduction to Slope Fields. And what we're going to do is create a field of slopes. And we study slope fields because when we're solving differential equations, sometimes you can't integrate every differential equation and come up with a solution for y equals. Sadly, not everything people have found a pattern for to find the antiderivative of. So there's this field of study called differential equations and the slope fields that you can actually look at a field of the slopes of tangent lines to the families of functions that solve a differential equation, and you can tell a lot about the function by looking at its derivative, as we all know. So what is a slope field? Well, slope field takes a differential equation, which happens to be an equation with a derivative in it. And this one is dy dx equals x plus 1. And this is a first order differential equation because it has a first derivative in it. So in order to create a slope field, we have to figure out what the slope is at every point. So let's choose a point. Let's try 1, 1 for simplicity. And if I plug in 1 for x, I get a slope of 2. So I'm going to put a microtangent line with a slope of 2 right there. There is my first slope. And then what you do is you figure out what all the slopes are all around this field. All right, so what happens at this point, which is 1, 0? Well, x is still 1, so the slope is going to be 2. So, and let's try this point here, which is the point 1, 3. Well, guess what? X is 1, so that point, the slope is still 2 there. So what's going to happen is when x is 1, all the slopes are 1. When x is 2, all the slopes are 2, so these are going to be a little bit steeper. And then when x is 3, the slope will be 4, which is even steeper still. All right, now, when x is 0, we have 0 plus 1, so we have a 1 slope. And then when x is negative 1, the slope at every one of these points is going to be 0. When x is negative 2, the slope will be negative 1. When x is negative 3, the slope will be negative 2, so it's a steeper negative. All right, so we have just created our first slope field. Now, when looking or analyzing at this slope field, you'll notice that this differential equation is dependent only on x. So I'm going to write that down. Dependent only on x. So if it's dependent only on x, all you need is the x value for each coordinate, and then you know what the slope is, which makes the graph very interesting because if you notice for every x, now I have these as integer values of 1, so this integer value. So all of these points are integer values. But you can have a slope field where you have slopes at fractional values too. So, or any real value, you can have a slope field. I just made these nice integers of 1, or integers to start out with. Okay, so this slope field is like I said, dependent only on that's an E, I'm sure. Dependent only on x because it has only an x in its derivative. All right, and so for every x, the slope is the same. Well, we call these isoclines. So the isoclines, iso meaning same, cline meaning slope. So isoclines are in the x direction. All right, so this has an isocline of the slope of 0 and 1, 2, 3, 4, and vice versa. Well, The other interesting thing about the slope field is by looking at the slope field, can you tell whether this function has any extrema or not? Well, I hope you say the answer is yes, because you can see that if you follow the flow of the slopes, that it looks like it's going to be having an extrema when x equals -1. So this represents the family of functions that are the solutions to this differential equation. So this looks like a family of parabolas, and it would be because we know the antiderivative of this is x squared over 2 plus x plus some constant. And whatever the constant is going to dictate which solution we have. But looking at the slope field, you can tell me that it has an extrema, and the extrema will be absolute, and it's an absolute minimum, and they will all occur at x equals -1. Why? Because the slopes on the left are negative, going to a zero slope, going to a positive slope. So that is, by the first derivative test, a relative or local, or in this case, absolute minimum. The other thing you can tell by this is that the curve is concave up. Just by looking at the flow of the slopes, then you can tell when this function is increasing. You know, it's increasing from -1 to infinity and decreasing from -infinity to 0 or -infinity to -1 because the slopes are negative. And so that tells a lot about the function if we weren't able to take the antiderivative of this, which is pretty interesting. So it's dependent on only x. That means the isoclines are in the x direction, and isocline means same slope. And we can just tell a lot about the parent function. And the family of functions here would be parabola. All right, I'm going to let you, well, we'll do the first couple together. All right, so this is dy dx equals 2y. So now we're going to find and create a slope field. And what I like to do is decide whether first is dependent on x or dependent on y. And in this case, this one is dependent on y only. So this means the isoclines are going to be in the y direction. Because it doesn't, this derivative here doesn't depend on x. So let's start off very easily. When y is 0, we have a 0 slope. So y equals 0 is the x-axis. So we are going to have a whole bunch of 0 slopes here. And when y equals 1, we're going to have slopes of 2. So we're going to have slopes of 2. Those are pretty steep. And then when y is 2, we're going to have slopes of 4, which are steeper even yet. And then when y is -1, we're going to have slopes of -2. So we're going to switch our slant here. To a negative slope. And then -4 is going to be when y is. So you notice the isoclines are in the y direction. And you might ask yourself, okay, so what family of solutions would this be? Well, it looks like we have two types of solutions. We have one solution that is linear. And so one solution would be the line y equals 0. That'll be one solution type. And then we have another solution type. So if we were going to pass through 0, 1, let's say, if we follow the slopes, it's going to look like this. So that'll be an exponential solution, a positive exponential. But what if the point were to pass through 0, -1? Well, the solution type would be a negative exponential if you were to follow the slopes. Okay, so this one has two solution types, this slope field. It has a linear solution type, and it has an exponential. Now, of course, that depends upon what our initial condition is when we solve the differential equation as to which solution you'll have. Okay. Isoclines, again, are all in the y direction because this slope field is dependent only on y. X plus y. This slope field is dependent on x and y. And this one is more challenging because we have to use the entire point when we are trying to figure out what the slope fields are, or what the slopes are at each point. So I'm going to give you a few minutes to figure out what your slope field should look like, because I've indicated how we do these. And so pause the tape or the video and you do your slope fields, and then we'll come back and discuss what you get. So pause. All right, let's see what you got. You should have gotten a slope field that looks like this. Now in the beginning, sometimes your slopes are a little bit off because you just miss a negative sign or whatever. So just check your slopes against mine to see if you think that they are correct. And once you get it straight, let's discuss what's happening here. Like I said, this slope field is dependent on x and y. So it doesn't have isoclines in the x only direction or the x or the y only direction. It has interesting isoclines. Hopefully you noticed right away that you have an isocline in this direction. To me, the ones that pop right out are the zero slopes. That's an isocline. So now we have the isoclines on the diagonals, which is interesting because this is a slope field dependent on x and y. This slope field has three different types of solution. It has a linear solution, which I hope you can see right away is this solution right here. It's a linear solution, and we can even see just by looking at the slope fields and not solving this, we can say we have a solution. We could read that equation right off because this is -1 and this is -1. We could read what this equation is right off the slope field, and that's going to be -x minus 1 is one solution. So we have a linear solution. And then we have a solution type that occurs above this asymptote because it becomes an asymptote when it's not a particular solution. And so let's try, let's go through this point here. And if we make that our initial condition, we can say we can follow the slopes. And you'll see that the second type of solution is going to look like this. And we can say it's going to have a minimum along this isocline because all the slopes here are 0. And they're going towards a positive, going towards a negative. So negative slopes to 0 slopes to positive slopes gives us a minimum on this side. So that's going to be a different type of solution. And then you're going to have a solution on this side that looks like this. So we have 3 solution types. And one of them is linear. I'm not sure, we don't know what this one is going to be because we can't find the antiderivative of this because we can't separate and integrate it. And so we know that one is linear, and then one is going to be a concave up solution, and one is going to be just an asymptotic curve-like solution. And the isoclines here are on the diagonals, which is very, very interesting. We can also tell when things are increasing and decreasing and where extrema are, which is pretty cool. All right, so that one has 3 different types of solutions. All right, this is another one that's dependent on x only. So what would your guess be? Isoclines are going to be only in the x direction. So I'll give you a second, pause the video, and you do your slope fields and see if you match mine. And we're back. I have done it ahead of time, and this is what my slope fields look like. These are a family of parabolas because if you take the antiderivative of 2x, you get x squared plus c. And this right here has only one solution type, and they would be of the parabola type. And I could have multiple solutions based on whatever you choose for an initial condition. So this too is a family of parabolas. Isoclines in the x direction and has absolute extrema, when all a family of functions would have extrema when x equals 0, which is pretty cool. All right, moving right along. Y equals -1. So pause the video, you come up with your slope fields for y equals -1, and see if you match mine. And we're back. Here is my slope field for y equals -1. This slope field is only going to be dependent on y, so this is going to have isoclines in the y direction. This one too is a family of exponentials and has two different types of solutions. It's going to have the linear type, which is going to be y equals 1. And then y equals 1 becomes the asymptote for the positive exponential solution and the negative exponential solutions. So another type of slope field. What's really cool is that you can see the asymptote and the linear solution all at once, and then you can see the increasing solution type and the decreasing solution type. So let's say your initial condition was up here. Let's say it was -1, 2. Then you know that you're going to have an increasing exponential as your solution. If your point was, let's say, 1, 1, you know that your solution has to be the line. If your particular solution was the point 2, 2, 2, -2, you'd know you'd have a negative exponential as your solution. All right, let's do another one, one last one. Y equals -x. Pause the tape and do your slope fields. All right, your slope field should look like this. This right here, believe it or not, is a family of hyperbolas. And since the solution to a differential equation must be continuous, you're going to be in one quadrant only. So this would be one type of solution. So if your point was in the first quadrant, it would be one type of solution, or this type, or this type, or this type. But the hyperbolas, the branches of the hyperbolas. Interestingly enough, when y equals 0, you have 0 slopes. So along the x-axis, you're going to have 0 slopes. And when x is 0, which is the y-axis, you're going to have vertical slopes or vertical tangents. And at 0, 0, when x and y are both 0, you don't have any slope because it's not defined to have 0 over 0. So there's no solution that will ever have 0, 0 in it. And so that's the family of hyperbolas. So what kind of problems might we see when we're solving or looking at differential equations or slope fields? Well, you might have a matching type problem. And this one says, match each slope field with the equation of this that the slope field could represent. So these are the parent functions, and these are the slope fields of their derivatives. So let's see if we can match them up. The first one is y equals 1. The derivative of y equals 1 is 0. So which slope field represents a slope of 0? Hopefully you can see that 7 goes with D, so we'll put 7 here. Now 8, y equals x. Y equals x has a derivative of dy dx equals 1. So the slope will always be 1. You see a slope field over here where the slope is always 1? Why, the answer is yes, and that one would be h. See how the slopes here are all 1? So that would be 8. All right, number 9. The derivative of this one is dy dx equals 2x. So I am looking for slopes that follow the pattern 2x. All right, or do you see one of these slope fields where you might see a quadratic in it? Well, that doesn't look quadratic. That doesn't look quadratic. That doesn't look quadratic. And that one doesn't look quadratic. Neither does E. So I think this one is the slope field, because and you can try a point too. At 1, 1, the slope would be 2. Do you see the slope is 2 here? And if you have x equals 0, dy dx equals 2x, these are all 0 slopes. So C has to be number 9. All right, y equals 1/6 x cubed. Do you see a cubic anywhere inside these parent functions or inside these slope fields? And I say, do you see the cubic here? So 10 has to be F. 1 over x squared. Back in the day, we studied power functions, and 1 over x squared looks like this. Do you see anywhere where you might see tangents to 1 over x squared? And I think that would have to be this one as a solution. So that would be number 11. Sine x. Do you see sine x somewhere? Imagine the slopes to sine x. And then sine x, remember, looks like this. It passes through the midline and looks like it has a slope of 1 and 0. So I think it's going to be this one. So sine x is 12. E is sine x, and then y equals cosine x. Similarly, it's going to have 0 slopes here, because you can see the cosine x function embedded in that. That's going to be 13. And then natural log of x has to be last but not least, 14. And you see ln x on this side? And when you have the absolute value of that, it's just going to be reflected over on this side. So that's 14. So that's seeing these functions inside the slope field. You can see y equals 1. You can see y equals x. You can see x squared. You can see x cubed in here, 1 over x squared. And then sine x, cosine x. It's just pretty easy to do. All right, the next one. Now I'm giving you the derivatives, and we're going to look at this, see if we can find the slope fields. So what I like to do when I'm doing these problems is look to see where the slope would be 0. And in this case, for 15, the slope is going to be 0 when x equals -2. So when x is -2, I'm going to have 0 slopes. So do we see anywhere on here where I have x equals -2 and 0 slopes? Well, I don't see 0 slopes here. I don't see 0 slopes here when x is -2. Oh, there it is. So 15 is going to be B. All right, 16. dy dx equals y. When y is 0, we're going to have 0 slopes, which is the x-axis. So I hope you can see that I have 0 slopes here. So 16 is going to have to be D. Now, when am I going to have 0 slopes? When x equals y for number 17. And do you see a slope field where I have 0 slopes along the line y equals x? And there it is. So that's going to be 17. And then this one is -x over y. When are we going to have 0 slopes? When x equals 0, which is along the y-axis, and I have 0 slopes here. And when y is equal to 0, I'm going to have vertical slopes, and you can see that we're going to have some vertical slopes here. And this is a family of circles, which is quite cool. So this one is 18 by default. So matching is pretty simple. I just look for the 0 slopes. All right. Another problem type you would get is the calculator drawn slope field for the differential equation dy dx equals xy is shown in the figure below. The solution passing through the point 0, 1 is also shown. Sketch the solution curve through the point 0, 2. All right, so I'm going to go to 0, 2, and I'm going to follow the slope fields. Well, there it is. There's would be my particular solution passing through 0, 2. So part A is done. Part B, sketch the solution curve through the point 0, -1. 0, -1. So there it is. Just follow the slopes. And they don't have to be perfect. They just have to follow the slopes. So we have a solution through 0, 1, 0, 2, and 0, negative 1. It's as easy as that. Last but not least, the calculator drawn slope field for the differential equation dy dx equals x plus y is shown in the figure below. Sketch the solution curve through the point 0, 1. 0, 1 is right here. And so I'm going to follow the slopes. And that would be through 0, 1. Kind of follows the flow of the slopes. And then the solution curve through 3, 0. Negative 3, 0. So that's 1, 2, 3 right here. That's those, then we're going to just follow the slopes. All right, can anybody tell me what the linear solution is going to be? Well, we already did this once. It's going to be the linear solution is this line right here. I'll use a different color. And a linear solution is going to be y equals negative x minus 1, just like the last one, because that's the same differential equation. All right, so that's all there is to slope fields. We'll talk more about how we actually solve the differential equations algebraically using separation of variables in the next lesson or two. So have a great day. Talk to you soon.